Welcome to episode 4 of Light.Conversations. Thank you for joining us. My name is Philip Constantine, and once again, we're joined by James Portman.
Hi, Philip. Hi, everybody.
Of course, the objective of today is to try and catch James out with some tricky questions. So let's see if we can achieve that. James, we ended off the last conversation on a question set around the speed of light and the speed of electricity, and how do we match these two as we design LiDAR devices. Now, if we look at the speed of light, it's commonly known that the speed of light is a universal constant, we're told, at 299 million meters a second. Is it really a universal constant?
The speed of light, as you see it written down with a small symbol c, is generally recognized as being the speed of light in a vacuum. Light is an electromagnetic phenomena, just like radio waves or anything else. It just happens to be a very high frequency electromagnetic phenomena. And the speed of electromagnetic phenomena is determined by the dielectric constant of the medium through which it's flowing. Now, we think of that in optical terms as being the equivalent of the refractive index. And in the case of a vacuum, you don't have to worry about the refractive index. Therefore, we have a nice constant number we can work with. Interestingly enough, the speed of light doesn't change very much through most ordinary media, like air, for example, and so on. We do know it changes through water because you get rainbow effects and refraction and so on. And those are caused by changes in the speed. But in the world of LiDAR that we spend most of our time dealing with, you can treat the speed of light as being very close to a constant, which is quite nice, because if you want to measure something, there's nothing better than starting with a universal constant.
Yeah, this is a good thing. I mean, given that, we've based the SI unit of 1 meter on the distance that light travels in 300 millionths of a second. So this is a good thing. Just talk to us about the frame of reference, right? Because the speed of light doesn't really change given your initial frame of reference. How does that affect design of LiDAR?
So this is where the world of science fiction and physics begins to overlap. And I think you have to be very careful about interpreting phenomena of different sorts. So, for example, we hear about things like redshift and blueshift, which have to do with very rapidly changing frames of reference. We also hear about things like time dilation and other consequences of the special theory of relativity. These are really exciting phenomena. And as an engineer, of course, you would like very much to exploit these phenomena if they happen to be relevant. So, for example, we mentioned the Lunar Laser Ranging Program of NASA during the late 1960s. Yeah. And one of the reasons for using light to measure to the moon was not only so you could see how far away the moon was, but so that you could look at time-space distortion between the Earth and the moon and see whether the theories of relativity, both the general and the special theories, held. In the world of LiDAR, we try and avoid rapidly changing frames of reference. In other words, you don't really want to be using your LiDAR at 10% of the speed of light, because it's a hell of a job to get up to that sort of speed. Instead, we rely very heavily on the consistency of the phenomena of light. And if I may just draw a quick parallel here, the same is not true when you look at sound. With sound, in fact, it's very easy to change the characteristics of propagation of sound through air. For example, the air pressure affects the speed of sound. The temperature affects the speed of sound. Humidity affects the speed of sound. In fact, many things get to be a big influence. Even the material that you're passing it through, if it's a gas as opposed to, let's say, ordinary air as we know it, that can also change the speed of sound. So it becomes more difficult to use.
That's interesting. I've always had a fascination with the Doppler effect. This is when an ambulance is rushing by and you have the wee 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 wee, and waveforms are stretched and compressed as a sound source moves. How is that reflected in light?
The same thing definitely happens in light. In fact, products like ring laser gyroscopes make use of the Sagnac effect, which is that you can simultaneously stretch and compress light within the same resonant cavity. Such a phenomenal idea where you can take concepts that are operating right at the limits of the laws of physics and be able to bring them down to the level where you can use them, in that case, for navigation. As exciting as the Doppler effect is, I think a lot of people are confused when they look at LiDAR into thinking that they do work with Doppler. Some of them do. For example, if you want to measure the velocity of aerosol particles high up in the atmosphere, you can use the color shift, which is the equivalent of a Doppler effect, on your laser in order to determine what those velocities look like. Most terrestrial LiDAR systems, however, where you're trying to measure distance, would not use that specific phenomena. But of course, it raises the interesting question of which phenomena are you going to use? We know that constant velocity is nice because effectively you have a ruler, but it's a ruler that works on time instead of on distance. In other words, you time how long light takes. And again, I'm sorry about this, but you tend to wander off into the nebulous realms of the time-space continuum, because whenever we talk about things at the speed of light, we tend to talk in nanoseconds. We don't tend to talk in meters. Because they're interchangeable concepts in the way that we're working. So you can think of a distance as being so many nanoseconds away. But from a practical point of view, it means that this velocity is the key thing that you're going to deal with. The wavelength itself, and the fact that the wavelength may change very slightly, might not be the key phenomenon that you actually want to deal with, or the phase shift for that matter, which is an equivalent concept.
Let's consider for a second now, as we move from light to electricity and charge. Electricity is commonly thought to be the movement of electrons. We do know that we look at Einstein's theory of relativity. I mean, any particle with mass, which is what an electron is not able to move at the speed of light. It can approximate, but it can't. If we look at electricity as a phenomenon, it's not really the electrons moving through the conductor, but it's the field and the electromagnetic field that is around the conductor that's moving, and the electrons actually move more slowly than the field. So what are the considerations as one looks at light and the speed of light and how unaffected light is, and then translating that into the movement of electrons and the fields around conductors and also tracks on a PC board?
Yeah, I think you're highlighting a really important subject here. At school, we tend to learn about subjects almost a little bit in isolation. So we learn a little bit about light by looking at rainbows and prisms and things like that. We learn a little bit about electricity by connecting light bulbs to batteries. We might, if we survive towards university, look at electromagnetic radiation in terms of radar and so on. But it's amazing how interchangeable these phenomena are. And because they're interchangeable, at any moment in time, you have to make a decision as to which aspect of that phenomenon you're using. In the case of light, is it a particle or is it a wave? In the case of the flow of electricity, is it electrons that you care about, or is it the electromagnetic field around the electrons that you care about? And it's a surprisingly confusing space, because at any one moment in time, you don't necessarily know which of these phenomena is dominating. So I'll simplify things a little bit and say that in terms of the propagation of light, we generally tend to worry about the electromagnetic propagation of light. In other words, not the individual photons, not the individual wavelets, but the group performance. In other words, a bunch of photons that you create and you send them out through the air or through space. How do they perform as an entity? Similarly, when we look at electricity, we tend to look at the net effect. In other words, I don't really care that much how the electrons got to where they are or which specific electrons are dealing with the phenomena. What I care about is how do I control the appearance of the electromagnetic wave and the signals that I get out of a conductor. And because the phenomena have a lot of parallels in the sense that you're dealing with electromagnetic radiation, there is always the temptation to think that you can handle them in the same way. But unfortunately, the frequency differences tend to make it a little more specialized in the sense that what works on a piece of light doesn't necessarily work on a piece of electricity and vice versa, because the duality then begins to trip you up. So when you're trying to measure phenomena which are occurring at the speed of light, in other words, how long does it take light to travel from point A to point B and back again? And the way that you're going to measure that is by using electromagnetic devices on a circuit board. You have to understand what you lose in that translation. That you're quite correct that the speed of the electromagnetic propagation on the circuit board is not the same as the speed of light. That even the way that the electromagnetic signal comes into existence is not necessarily the same way that the optical signal came into existence. In other words, they're not an exact mirror of each other. And you clearly have to convert between the two domains. One moment you're dealing with optics, the next moment you're dealing with electronics. And how do you get between the two? And how do you get between the two efficiently? This is a tricky subject.
Right. And if we zoom in a little bit now, I mean, that converter in the world of LiDAR is a detector. So that the detector is what converts light energy into electrical energy. So maybe let's think for a minute around detectors and how they do so in an efficient manner.
I think the short answer to that is very poorly. We would like to think that the conversion of from photons into electrons is a well understood and a well controlled phenomena. And to most engineers and scientists, I think it is, because you're not looking at these phenomena at the limit. In other words, right at the very speed of light. You'd like to know, for example, is a light on or is a light off? So you go to your light switch, you turn the light on, and sure enough, you get some electrons coming out of a pin photodiode, for example, and everything looks pretty cool. But like everything in the world of physics and everything in the world of electronics, as you begin to look deeper and deeper, you realize that there are a lot of imperfections in this conversion process. So, for example, even at full efficiency, it turns out you only get one electron for every 2 photons. In other words, you only have about a 50% conversion efficiency. And it almost doesn't matter what you do. You're not going to do much better than that. It's kind of a photoelectric effect, and this is what you get. That doesn't mean you can't make sensitive detectors. But it turns out that the detector concept is not a single element. It's not like you can have just one piece of silicon and that's it. It's all sorted out. You have to start by saying, well, let's collect the light, let's collect the photons, let's collect the electromagnetic radiation that is light and focus it onto the detector. So the first element of your detection is your optical system, in fact. Think of it as an optical amplifier. I know it's only a lens or a lens arrangement. But what it's doing, though, is it's making the signal bigger on an optical level. And the bigger the signal you get, the more electrons you're going to get out. What is very nice about optical systems is that they are relatively efficient, meaning that they add a lot more signal than they add noise. And this is very important because electronic amplifiers are not the same. So kind of rule 1 in LiDAR design, if you can amplify optically, do it. The last resort is to amplify electronically, because electronic amplifiers are horrifically imperfect at the speeds that we're talking about. So, go ahead.
No, please.
All right. So, when you look at a detector and you realize that it's not that efficient, and you've thrown as many photons at it as you can, you would probably make the assumption that the electronic response would match the optical response. Meaning, as the signal grows, so the number of electrons would grow in proportion to the number of photons hitting the surface. It turns out this is not true at all, that in fact detectors have a speed limit. They can only respond so quickly. Photons, on the other hand, are effectively instantaneous if you can create them that way. In other words, you can talk about sub-picosecond phenomena, femtosecond phenomena, really quite easily. But to make a detector that can operate in the femtosecond region is really tricky, because electrons, they're very sluggish. They really don't like to move. You can imagine you've got a child's playroom full of magnets that are all joined together, and you come running in as a 5-year-old and you grab the first magnet. You can imagine what a slow and sticky process it is for these magnets to transfer the information to each other so that the electromagnetic propagation takes place. As engineers, we're not taught very much about this. I must admit, we're always taught that, electricity is this amazing thing and it's like super fast and it does wonderful stuff. But the moment you talk about this conversion of light to electronics or to electrical circuits, everything goes out the window. not only does the performance of the detector become a problem, but the moment you connect something to the detector, all the characteristics of what you've connected to it begin to influence the performance of that detector. And what seemed like on paper, when you read the spec sheet, super high performing detector, once you built a circuit to make it work, what you tend to get out is a little lump instead of this super high speed spike of energy that you were looking for.
That's interesting. And of course, this is a function of the inertial momentum of those electrons themselves, that we don't have this instantaneous move.
Interestingly enough, electrons themselves individually are pretty quick. It's when you get them all together, it's like herding sheep. They just want to do different things than you're trying to tell them to do. So whilst each individual electron is bouncing around like mad, the net electric field that you get suffers from stray capacitance, stray inductance, interference from other directions. And because you have a physical device here now, you have a physical electronic circuit with tracks on it, it's that physicality that constrains the performance of the electrons.
Thank you. Just in closing, I'd like to ask a question. If we have these very different characteristics around light, around electricity, around the sensor that is the segue between the two and gives us this photoelectric effect, how does one begin to choose a laser for the very different modes of operation in each of these areas?
This is certainly something that trips up most designers. They make the assumption that you can either choose a laser or you can choose a detector or you can choose an amplifier, and each one is an independent device. The real trick on these things is to look at the characteristics of all of these devices together. Look at your laser and see how it influences the performance of the detector. Look at your detector and see how it influences the performance of the amplifiers that follow. Look at your optical system and see how it affects the entire signal chain. Unless you look at it from a systems level point of view, you could end up with a laser which is super fast, talking to a detector that's super slow. And you've completely lost the value that you may have had from a high-speed signal, for example. Or you could have a laser that has very low power, only to discover that the sensitivity of your detector is so poor that it can't receive the signal anyway. It is not a trivial answer. It is a problem space, if you like, in which there are many answers. And as an engineer, our job generally is to try and find the sweet spots within that space so that we can say a certain combination of components has a certain level of performance at a certain price, which will therefore finally meet the expectations of the customers so that their application can be solved.
Not an easy problem to solve. James, thank you so much for your time today. I've learned so much, and I'm sure our viewers who are out there designing their own LiDAR systems will have learned some tips and tricks today. So thank you for your input and your wisdom, and appreciate your time today.
Thanks, Phil. Great fun as always.
Right, that's it for today, viewers. Thank you so much for joining us. I'm sure you learned a lot, as I did. Next week, I will question James on issues around amplification and amplifiers. Let's discover more around optical amplification, around electrical amplification, and see what we can learn. Please subscribe to our YouTube channel and see you next week. Thank you. Hi viewers, we've got some really great news for you this week. We're launching the brand new SF000 Micro LiDAR. It's a truly remarkable product which breaks all the boundaries in terms of size and weight. And you know what? To celebrate, we're going to give 2 lucky followers a chance to win this exceptional sensor. So please join us at the webinar. Click on the link below. You need to register for the webinar and stand a chance to win this amazing product.